Hello dear friends, we continue our discussion on layout design and we continue our discussion on the algorithmic approach for layout design. So in today's lecture we will talk about construction algorithms. We will talk about the basic steps of these construction algorithms and these algorithms, these steps include a selection and a placement. So what are the different methods or different procedures to use in the selection of departments, and then what are the rules that are used in the placement of these departments. We will talk about alternatives like the CORELAP and ALDEP selection and placement procedures. So let's get started. We already talked about construction and improvement algorithms. So we said that the algorithms can be classified as construction and improvements. And what were these? The construction algorithms basically start from scratch. There is no layout in your hand and you follow a number of steps, and at the end of these steps you reach to a feasible layout. So graph-based method that we already seen, and the CORELAP and ALDEP that we will talk about can be given as examples of construction algorithms. On the other hand, in improvement algorithms, you already have an initial layout. Okay, either you find it by yourself or you already have your facility working. It has an initial layout and you want to improve it. Okay, so you start from an initial layout and try to improve it. And a pairwise exchange method, a craft algorithm, or the MC craft algorithm that we will talk about, can be given as examples of improvement algorithms. In this lecture, we will talk about the construction algorithms. So the basic steps of construction algorithms can be given as follows. Assume there are n departments that are going to be arranged in this layout design. Okay. For example, there are 10 departments or 5 departments that you want to find the layout for. Okay. So what are the steps of this algorithm? We can give the steps like this. For each department from 1 to n, we select a department which is not yet placed in the design, not yet placed in the layout. Okay. Select one of those departments. We will talk about how to select this. And then the second step is to place this department to a suitable place in your layout. Okay. So you repeat this step again and again. You select the first department, place it. Then go back, select the second department and place it. And do this for all the departments that you need to design. Okay. And this select and place procedures may differ from one algorithm to another, and we will see the alternatives of these selection and placement procedures. Let's start with the selection rule. Selection specifies the sequence of department placement. Okay? So when you start by selecting the first department, it will be the first one to be placed in the layout. Then somehow with a rule you select the second department, and it is the second department which will be placed in your layout. Basically this selection can be just random, okay? Without looking at any attribute of the departments, you just select one department and place in the layout, and then select another department randomly and then place it in the layout, and it works. And if you try this several times, I mean, you do complete the algorithm one time and come up with a design, and then you restart the algorithm. Since the selection is random, it means that every repetition of the algorithm will provide you a different sequence of selection, and then the final layout will be different. Okay, so it can be an alternative selection procedure, I mean randomly selecting. But you may include some intelligence in this. For example, in ALDEP is one of the construction algorithms that we will talk in detail. How we select? in ALDEP, okay, the first department is selected randomly. If there are, for example, 10 departments that you will find the layout, you select the first department randomly. And then when you are selecting the second, third, the other departments, what you look at is, you look at its relationship. Okay, if it has a relationship of A with the previously selected department, or let me say in this way, you specify a threshold value. It can be A, absolutely necessary, or E, especially important, and etc. Okay, so there is such a threshold value, and then you find all the departments that has a relationship better than this threshold value. Then what do we do? Among all these departments, you select one of them randomly. Okay, let me try to explain more specifically. Let's assume that you selected department 2 as the first department. Okay, then for the remaining departments, you find all the departments that has an A or E relationship with department 2. So my threshold here is E, okay, especially important. So I find all the departments that has A or E relationship with the previously selected department, which is 2. Assume that department 3, department 5, and department 7 has this relationship. Then I select one of these 3 departments randomly. Okay. So if there are no such departments exist, so there are no departments having an A or E higher than the threshold value relationship with the previously selected departments, then you select one of the departments in the remaining list randomly. Okay, so this is how we apply selection in ALDEP. We will make examples of this. Okay, so CORELAP is another construction algorithm, and the selection procedure in CORELAP is different than ALDEP. Okay, in CORELAP, it defines a total closeness rating, which is shortly TCR. Okay, so what is this TCR? It is the sum of the weights for the relationship between the department and all other departments. So for each department, we calculate the TCR. And in order to calculate this TCR, we check its relationship, the relationship of this department with all others, and we take the sum of these weights. Okay. So then we have these TCR scores for all of these departments, and then we select the department with the largest TCR as the first department to be placed. This is an example showing how to calculate this TCR. So in this table here, we have 5 departments, okay? And it shows the relationship between or among these 5 departments. The relationship between department 1 and 2 is U, 1 and 3 is E, and etc. And in this question, it's given to us that for a relationship, we are going to use a weight of 6. For especially important, we will use a weight of 5, and as such. Okay, so this is given to us. You see, in this example, for X, which is undesirable, a weight of 1 is used. But remember, for example, in ALDEP, we said that for X relationship, we are penalizing it. We are giving a weight of minus 1024. But here it's not negative, but it's positive. So different algorithms or different layout analysts may use different weights for these relationships. Okay, keep this in mind. In this question, we are going to use these weights. Then how to calculate the TCR scores for all of these departments? Let's first look to the first department. Okay, so the first department has U relationship with 2, it means that U relationship according to the weights given is 2. What about E? It's 5. What about important? I, it's 4. And what about U? It's 2 again. So when you sum up all these scores, 2 plus 5 plus 4 plus 2, we obtain a TCR score of 13. Okay, so for the second department, again we need to calculate the TCR score, but be careful while calculating it. Since this matrix is symmetric, only the upper triangle is given to you, but you need to consider all of it. So this let me show. This cell is empty here, but in fact it is not empty. It is the same with this one since it's symmetric. So while calculating the TCR score for this department 2, you should consider that there is U here, and its score, its weight is 2, and this A is 6, and ordinary important is 3, and this also 3, and when you add up all these weights, you come up with a TCR score of 14. Okay, so this is the TCR score for department 2. And we calculate the TCR score for each of the departments. And then in CORELAP, the department with the highest TCR score is selected first, which is department 3. Okay, selection is the first procedure in many of these construction algorithms. And we have seen that in different algorithms like ALDEP and CORELAP, we may use different methods to make this selection. But after the selection, after determining the next department to be placed in the layout, you need to find a way to place that department into your layout. How can we do this? And the placement is in fact not very easy. It's difficult because there are many different alternatives that you can use during placement. For example, let's consider that there are n departments to be placed in our layout. Okay, and let's consider a very simple example. Assume that each of these n departments have the same area. Okay, all of them requires, let's say, 10 meters square, and all of them will have a square shape. We also, let's assume that this is the case. It's very simple case. Then if you want to find a placement, in total there are n factorial different alternative ways to lay out these departments, n factorial. And this n factorial in fact is a very large number. Look, if you have just 10 departments, 10 factorial makes this huge number. Okay, if you want to find the best layout, then you may need to evaluate all of these alternatives according to their adjacency based or distance based scoring that we have seen in previous lectures, and you need to select one of them. But you see, it's a huge number even for a very small number of departments. If you increase this number to 20 or 30 departments, this number will be huge and it's impossible to calculate those. And you see, this is a very simple example in which all departments have the same area and have the same shape. But in fact, you can change or in real life, the shapes of the departments and their sizes may be different, which complicates the problem even more. Okay, and also in that case, when you have different sizes and different shapes, then we need to consider some what are the feasible shapes of departments. Can every shape be considered as realistic, practical or not? So let's talk about these shapes a little bit more. Okay, so we will talk about some rules for the departmental shapes. But first, let's remember, in order to represent the departments in the computers or with the computers, we said that we use smaller grids. Okay, and while placing the departments, in these construction algorithms, again, we are going to in fact place these smaller grids. And the number of grids multiplied with the unit square area of these grids or unit squares should give you the size of the department. Okay. Then while placing these grids, the question is, can we place them as we like? No. In order the department shapes to be feasible, you need to satisfy some rules. And first of these rules is the contiguity rule. Okay, contiguity rule. What does it say? It says that if a department is represented by more than one unit area square, like this. So this department is represented with 3 grids or 3 unit area squares. Then every unit area representing this department must share at least one edge, okay, with at least one other unit square. Okay, let's have a look at this shape. All these unit area squares represent the same department, but you see this grid or this unit area square does not share a common edge, common side, either this one or this one, with the others. It's just connected through the corner. And according to this contiguity rule, it's not feasible. Okay, this department can be on this side, like let's say this, or it can be here like this, or can be here like this, like this, like this, or like this. In all these red ones, the red unit area square share an edge here or here or here, you see. But this one does not share such an edge, so the contiguity rule is not satisfied in this shape, and therefore this is not a feasible shape. Okay, this is the contiguity rule. The second rule is the connectedness rule. Okay, in the previous one, even if the square areas are connected, they are touching each other, but if they are connected from the corners but does not share a border, then the contiguity rule was not satisfied. On the other hand, of course, the departments should be connected. So, for example, when you look at these 4 unit area squares, they are representing the same department, but you see they are not connected, as if they are 2 separate departments. Of course, this is not realistic and this is not practical. That's why this connectedness rule is not satisfied here, and that this layout is not feasible. More formally, we can state this rule as follows. The perimeter of a department, so if we start the perimeter, let's say, we walk around the perimeter, okay, then we turn here, then we turn here, then we return here, okay, but this is the perimeter not the whole department, but it's only one part of the department. But in fact, the perimeter of a department must be a single closed loop in order to satisfy the connectedness rule. Okay, so this is important. Other than the first 2 rules, which are very important, we have some other rules as well, and these are also practical and realistic rules. For example, the first one of them is the enclosed void rule. Consider such a departmental shape. What do you think? Is it realistic? I mean, you see a department having such grid structure in which inside it there is another department. So this department, this empty part here, it's the enclosed void and it's not accepted. Okay, so that's why this is not a feasible placement for a department. The problem may not be this part here, but the problem the part here. Okay, the empty area here, it is not a feasible department shape. It doesn't satisfy this enclosed void rule. So another rule can be the shape ratio rule. Maybe this is not a feasibility rule, but it is a realistic rule. And what does it say? It says that the departments, in order to have a feasible shape, the greatest length to its greatest width should be within a specified limits. So let me give an example. If you have a department with 10 grids, okay, then if you make this department like this, having 10 grids on a single, let's say, line, okay, assume there are 10 grids here, then you see it is not realistic to have such a long and narrow department. And this shape ratio rule tries to avoid it. And what's the shape ratio rule? You divide this length to this width, which is 10 divided by 1, okay? And you say that it's not acceptable. The length divided by width, for example, you say that it should be at most 3 or 4. So you can give such values. In that case, such a departmental shape is not allowed. Okay? The ratio of the length to the width should be within specified limits. Another one, again a practical one, maybe still it can be considered as a feasible department, but it will not be realistic, is the corner count rule. Okay? So it says that the number of corners of a feasible shape may not exceed a specified maximum. And this rule tries to avoid departmental shapes having such a structure. Let's assume that we have a department having one grid here, another grid, another grid, then another grid, another grid, then like this and like this. Okay. So these are all, this is the shape of the same department. Okay, these are grids like this. Okay, so if you have such a shape for a department, it's not practical, and basically you count the corners. Okay, this is the first corner, second corner, third corner, fourth corner, fifth corner, and etc. You count all the corners, and you say that this number of corners should be less than or equal to some value. Of course, if in real life, if it's a rectangular shape, we want the corners to be equal to 4. But in some cases, maybe L-shaped departments are allowed or T-shaped departments are allowed. Then you can increase the number of corners accordingly, but it shouldn't be something like this. Okay, so the corner count rule tells you this. As we said, this placement is very difficult. Okay, we have such rules, but still these rules does not solve the problem at all. We still need some more additional rule. For example, consider this. The department, let's assume that, is represented by 4 unit area squares. Okay, so the question is, how many possible shapes are there for a department which is represented by 4 unit area squares? Okay, in fact, there are 19 different shapes. Okay, these shapes are illustrated here. For example, it can be 4 unit area squares can be formed in this way, or in this way, or in this way, in this way, or in this way. They all satisfy the previous rules. Plus, okay, you can take the mirror images, all of these, turn them. Okay, so if the shape is such an L, you can have that L shaped something like this as well. Okay, so this shape and this shape is still different. So when you count all of them, you obtain 19 different shapes. Okay, we can place these 4 grids, 4 unit area squares in 19 different shapes. And let's assume that we are going to place this 4 unit area square in a layout of 6 by 10 area in total, okay? 6 by 10. We are going to place this. And there are in total 304 different possible placement options, okay? So this is a very small example, a department with only 4 unit area squares, and the total area is represented by only 6 by 10. Even for this smaller area, there are these many different shapes and different placements. So placement is difficult. And again, even if we satisfy the previous rules of placement, we may end up with an infeasible placement into our layout. How can it be? Let's consider, for example, that this is our total area, and we are going to place, let's say, 5 or 6 departments into this area. Okay? Remember, in construction algorithms, you first select the department and then place it. Okay, let's assume that this is the first department that we selected and we decided to place it here. Then we select another department and place it to here. Okay, then we selected a third department and place it to here. Now what happened to this total area? So it's divided basically into 2 disjoint parts, okay, into 2 disjoint segments. Then we have the, let's say, 5th department or the 6th department. When you look at their sizes, both the 5th and 6th departments can be larger than this area. Okay, so in total, when you add up this, the size of this area plus this area, it's okay to fit department 5 and 6, but alone, none of department 5 and 6 can fit into this area. Then if you divide your total area into such disjoint sets, then it may not be feasible to end up with a layout design. Okay, so then we need some other placement rules. For this purpose, basically, we can use 2 approaches. Again, ALDEP and CORELAP can be given examples of these 2 approaches. One is the bounded placement rule. Okay, so in this bounded placement rule, we will still use the boundaries of our layout. Okay, we will use that boundaries, but we will try to place the departments into this bounded layout in a way that it will not cause in such disjoint sets and etc. The result will always be feasible. Okay? So we will use some simple and robust rules which will end up with a feasible layout configuration. But such rules may end up with different or weird departmental shapes at the end. ALDEP is an example of this, and we will make use of this ALDEP, show you the placement of ALDEP, and you will realize what is it. The second one, okay, the alternative to this bounded placement rule is the free placement rule. And in this free placement rule, you forget about the shape or the size of your total layout. You just place the individual departments without considering the boundaries, and you come up with an initial design. Then you modify the design to fit into your shape. Okay, and CORELAP can be given as an example to this. Again, we will show these ALDEP and CORELAP in more detail. Let's start with the ALDEP. We said that in ALDEP we consider the boundaries of the total layout, and we use a bounded placement procedure. For this purpose, we have this the so-called sweep width. Okay, ALDEP uses such a width. The user gives this width as a parameter of the algorithm. When we make example, it will be clear. So by this sweep width, we in fact divide the layout into a series of lanes. Okay, in the next slides you will understand it. Then the placement rule starts from one corner of the layout. Okay, let me sketch. Let's assume that this is our total layout. Okay, so with this sweep width, in fact, we divide this total layout into a number of lanes. Okay, so this length here is the so-called sweep width. So they are all equal to each other, all these lengths. And then ALDEP starts placing the departments starting from one corner. It can, for example, start from here and places the departments, the grids of the departments here. And as soon as it reaches to the bottom, then it continues from the next lane. And then it continues with the next lane in this manner. Okay, so the departments are placed in such a way so that it never exceeds the boundaries of the department, and also there are no disjoint segmentation of the total layout. This is an example of ALDEP. As I sketched, you start from one corner and place the departments, and then you pass to the other lane and continue to place departments. Whenever the total number of grids for a department is finished, then you immediately start with the next one. Remember, in construction algorithms, you select and then you place. So what happens? Assume you first selected department 1. Okay, so you start placing the grids of department 1 to here, and assume that this department 1 requires 6 grids. When you finish with these 6 grids, then you select the next department. Let's assume that it's department 5, and you start with department 5 and placing its grids. And department 5 may require, for example, 5 grids. When you complete it, then you start with the next department. Let's assume that 3. So you continue with 3, and as soon as you finish placing the departments of 3, then you continue, let's say, with the next one. And as I said, as we said, in this kind of bounded placement, the departments may still have such weird shapes. So for example, look at the shape of department 3. It's something like this. You see, it's feasible. The continuity rule, the contiguity rule, and connectedness rules are satisfied, but the number of corners is a little bit larger, and it may not be too much practical. And this is another example of a departmental shape. So we may end up with such a department. You see the number of corners, this one plus this one plus this one. Okay, the number of corners is too much, and such a departmental shape can be not practical. But the resulting departments in ALDEP or in this procedure depends on your sweep width. So if your sweep width is this much, then you may end up with such a shape. But the sweep width, the width of this lane, is given by the user. And instead of using such a sweep width, let's say if the sweep width is 4, you can use a sweep width of 6 instead. And your lanes will be like this. Okay, this will be first lane, and let's say this will be your second lane, and etc. And then you will end up with a different departmental shape. So you can try different sweep widths, and then at the end you will end up with different layouts, and you can select the best one of them. Okay, let's consider this example. Assume we have a total area of 5 by 8 squares, and department A requires 10 squares, department B requires 5, and C requires 13. So let's assume that in ALDEP we are using a sweep width of 2, which means that we will divide the lanes with length 2. This is first lane, this is second lane, this is third lane, and the other one is the fourth lane. Okay, so we will start with placing A. Let's assume that the sequence of placement is determined as A, B, then C in this order. Okay, so what we will do, we will start from this top left corner and start placing department A. This is the first square. This is the second square. Okay, then we continue here, third and fourth. Okay, we continue fifth, let's say sixth, 7, 8, 9, okay, and 10. So we allocated 10 for A. Then, since A is finished, we will continue with B, and we will start allocating grids for B. This is 1, 2, 3, okay, 4, and 5. You see, we move in this order from here to here, then to here, then to here. Okay, then 5 grids are allocated for B. Then we start with allocating C. Okay, C, 1, 2, 3, 4, 5, and we continue in this way allocating the grids. Okay, so this is how we find the layout using ALDEP with a sweep width of 2. And this is the final layout that we find if we make this allocation with a sweep width of 2. So the department A has a good shape. It's rectangular. Okay. Length to width dimension can be a little bit narrower or larger, but still it's rectangular. But for B, you see we have an L shape like this, the department shape. It's also acceptable. And for C, the department shape appeared to be something like this. You see the corner count for department C is a little bit larger. You see from here to here to here to here. These are, let me show. This is one corner, another, 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 and another. And these corners also. The department C's shape is a little bit weird, but still we can use this as a feasible layout. Okay, now let's consider the same problem, exactly the same problem with a sweep width of 4 this time. So we divide the total layout into 2 lanes, okay, with a length of 4. So this is the first lane. We will start from this corner and place 10 A's. So this one A, then another A, third, fourth, 5, 6, okay, 7, 8, 9, and 10. When we finish with A's, we will continue with B. Okay, we will assign 5 B's, 1, 2, 3, 4, and 5. Okay, then when we allocate 5 B's, then we will continue with allocating C's. Okay, in this way, and we continue, we pass to the next lane, and when we are at the end, we will continue here and allocate 13 such C's. Okay, this is the solution. Of course, you will continue until you allocate all 13 grids, squares. This is the solution of ALDEP or bounded placement with a sweep width of 4. You see how the layout changes with the change of the sweep width. You see, this is the final layout with the sweep width of 4. This is the shape of department A. Now it is not rectangular. Department B has such a shape. And you see department C has this shape. I don't know if this is preferable to the previous alternative or not. But still, we end up with a different layout alternative. So changing the sweep width leads to different alternatives. As you can see, ALDEP has a meaningful, simple rule that leads to a feasible layout at the end. But different than this, CORELAP has a very different logic. As we said, it uses a free placement. And how this free placement rule works, in fact, it evaluates a number of different locations for the departments to be placed. And also, it evaluates different rectangular shapes for the departments. Okay? So how it starts? It selects first department and it places the first department in the middle of the layout. And then it selects the other departments one by one and places these other departments around the first department. So the shape starts from the middle and grows accordingly, and there are no boundaries for this. While selecting the most suitable place for a department, CORELAP uses two criteria. One is the placing rating and the other one is the boundary length. So let's see some examples. Okay, what's placing rating? Placing rating is the sum of the weighted ratings between the new department to be placed and its neighbors. Okay, so we will make examples, but let me show you. Let's assume that you initially placed this first department. Let's say it's department A. And then you also place department B like this. And now you are going to place department C. Okay, so if we place department C, depending on its size, of course, like this, you see C is a neighbor of A, and also it's a neighbor of B. Then the placing rating of C to this position is, since it's both neighbors of A and B, you take the relation between A and C if they have an, for example, especially important relation. You take that relation, and also let's assume that there's an ordinary important relation B and C. Okay, you take these two, O and E, and calculate the sum of their weights. So this is your placing rating for department C to this position. But in fact, if alternatively you place department C to here, now C is not a neighbor of B, but C is a neighbor of only A. Then the placing rating for A will only be the equal to the weight between the relationship, the weight of relationship between A and C. Okay, this is placing rating. So what is boundary length evaluation on the other hand? The boundary length is this. When we place, for example, department C to here, they share a common boundary from here to here. Okay. Let me show in a different color. This boundary here is shared. Okay. Then the length of this boundary, which is shared, is the boundary length. On the other hand, let's say we decided to place department A, department C to here. Let's say, okay, this is department C, and the boundary shared with A is this side, and the boundary shared with B is this side. So the total length of the boundary that this C shares with the previously placed departments is this side plus this side. Okay, that is the total length of the boundary. So CORELAP uses these two criteria while selecting the most suitable place for a new department. An example will be helpful in understanding. Let's assume that while this CORELAP algorithm, we already placed departments 1, 2, and 3. Okay, we already placed them, and their initial shape or placement is like this. We started with department 1 and then decided to place department 2 to here, and assume we decided to place department 3 here. Now we are going to place department 4. Okay, so the relationships between these departments and their weights are given. Now we are going to place department 4, and this department 4 has an absolutely necessary relationship with department 1, and it has an especially important relationship with department 2, and it has an important relationship with department 3. Now we will consider some alternative locations for this department 4 and calculate it's boundary length and placing ratings. So as a first alternative, let's consider this. Placing department 4 to here. Then what's the placing rating? In order to calculate it, we need to look the neighbors of this one. Okay, when we place in department 4 to this position, it's neighbor to department 1 because they share a common border, and it's also a neighbor of department 2 because it shares a common border. And remember, the relationship between 4 and 1 was A, so we have an A relationship here, and the relationship between 4 and 2 was E. Okay, so 4 is not a neighbor of 3, that's why we don't need to consider their relationship in this placement. So accordingly, the placing rating will be the sum of the weights of A and E. And remember, A was 600 given to us as 600 and E is given to us as 200. So it means that the placing rating for this one would be 800. On the other hand, what's the boundary length? The boundary length will be equal to this length that it shares with 2 plus this length that it shares with department 1. So this length is 3 meters. From here we understand it. And what about this length here? In total, we have 6 meters here. Okay. And 2 meters is here. 3 meters is here. Then 1 meter remaining here. So 3 plus 1 makes the boundary length as 4. Okay. So for this alternative 1, the placing rating is 800 and boundary length is 4. Let's consider an alternative position, alternative placement. Assume now we are placing department 4 to this position here. And now it shares the border with 3, and the relationship between 4 and 3 was important. Okay, I relationship. Sorry. And between 4 and 1, the relationship, it is neighbors, they are neighbors, and the relationship was A. Then the placing rating will be the weights of A plus I, which is 600 plus 600 for A plus 50 for I, which will make the placing rating as 650. On the other hand, what about the boundary length? The boundary length will be equal to this total sum of the length that this department 4 shares with the previously placed departments. So we know that this is 2 meters from here, right? Then, since the total length of this department 4 is 3 meters, we know it's 3 meters, then the remaining length here is 1 meter. So 2 meter plus 1 meter here, it makes 3 meter. So the placing rating for this alternative is 650 and boundary length is 3. So where do we want to place a department? We want, of course, the placing rating to be higher as much as possible and also the boundary length to be higher as much as possible. A higher placing rating and a higher boundary length is a better alternative. Okay? So when we compare these two, you see alternative 1 has a placing rating of 800, which is greater than alternative 2, and has a larger boundary length, which is 4 greater than 3. But in fact, we can place this department 4 to anywhere on the perimeter of the previous departments. For example, we can place it here. We can place it here. We can place it here. Or we can place it here. We can place it here. So you should try any one of those places calculate the placing rating and the boundary length, and depending on those, you need to select where to place this new department.